So today the next talk is about Professor Wei Li, and she will tell us about the BPS shifted to Yangians and the presentations from colored crystals. Please start.
Okay, so this is my title. So first, I would like to thank the organizer for inviting me to speak here. And so this is based on the work with Masahito Yamazaki here, and also some work in progress, but hopefully finishing soon, with Dima Galakov and Masahito Yamazaki. Also, this is a paper that's closely related to this too by Dima Galakov and Masahito Yamazaki. So this is the setup. So we consider type 2A strain in a generic toric clubule threefold, and look at the BPS sector, which is given by this deep brains wrapping holomorphic cycles of this threefold. So the main question we want to ask is what is the BPS algebra underlying this BPS sector? And then what can we use this BPS algebra for? The main result is that so this BPS sector can be described by a include 4 quiver quantum mechanics. So from there, you can see that the BPS states are given by certain colored crystals, and the BPS algebra should act on this set of BPS states. And from this action, actually, you can bootstrap the BPS algebra, and the resulting algebra are some quiver Yangians, which are given by this quiver and superpotential pair. So the advantage of this construction is we can get the explicit algebraic relations for arbitrary for generic toric clubule threefold. So so this middle step, once you get this quiver Yangian, actually you can forget about this middle step. So you can use this quiver and superpotential as the input, and then you can just directly write down this quiver Yangian. So it's basically just one page. So so in the previous slides, this quiver and superpotential pair is so-called canonically framed. So basically that means that we're only considering the closed BPS states, and it's in the non-commutative DT chamber. So the set of BPS states of certain molten crystals from this so-called canonical crystal. So they correspond to the vacuum representation of the this quiver Yangian. So for the second part of the talk, I will consider generic subcrystals of this canonical crystal. And so the molten crystal from this subcrystal correspond to non-vacuum representation. And also it's not the original quiver Yangian, but you can get some shift. So also I'll show that this subcrystal correspond to the framing of the quiver and superpotential. So this will cover all the non-BPS counting problem, all these other cyclic chambers, and include the open BPS states, and also many more representations. Yeah, I think that's it. That's it for the elevator pitch part. So now, so the plan to talk is that I'll first explain what is this BPS crystals, and then I will show how to construct this quiver Yangians, and then I will explain these representations that one can construct using these subcrystals, and then I summarize. So this is the system we want to consider. So it's a type 2A string compacted on a toric clubule threefold. So so this is the toric diagram here. So this is a simple case, the C3, and then roughly speaking, there are two types. The one where the toric diagram has no closed loops, corresponding to the toric threefold that has no compact four cycle, and those with a closed loop corresponding to the threefold with a compact four cycle. So the 4D series some include 2 quiver gauge 3, and the BPS sector is this D branes wrapping holomorphic cycles. So here we considered the case where there's only one D6, and for generic D2 and D0. And so so most of the talk I will consider the case when D4 there's no D4 brane, and actually so having D4 brane correspond to the truncation of the algebra. So the question is, what is the BPS algebra underlying this BPS sector? So to see that, we have to first describe this the BPS states in the BPS sector. So the effective description of this BPS sector is the include 4 quiver quantum mechanics. So the quiver is consists of a set of vertices, and also the errors from the vertices. So for each vertex correspond to a gauge group, and each error from A to B correspond to a bifundamental of the 2 gauge group. And also where there's the superpotential, which is given by the monomials of the bifundamentals here. So the information of the quiver and superpotential can be packaged into a periodic quiver. So periodic quiver means you draw this quiver on T2. So the fundamental and then you look at the fundamental domain. So this Q2 is the loops or the phases of the in this fundamental domain. So for each loop, you have a term in your superpotential, and the sign is for each arrow, here's there's a factor here, and the sign is given by this orientation of the loop. So for example, this the C3 case. So this is the quiver and superpotential. So you see this, the 2 terms correspond to the 2 phases in this fundamental domain here. So now from the quiver quantum mechanics to the BPS crystal, so we look at the torus invariant state of this quiver quantum mechanics. So it turns out it's given by the path algebra of Q modeled by the F-term constraints. So this can be described by certain 3-dimensional colored crystals. So the colors correspond to this the vertices. So there's a 1-to-1 correspondence. So for each crystal configuration, it corresponds to a certain D brane bond state with 1 D6 charge and a certain combination of D2 and D0. So the crystal generating function can reproduce the BPS partition function. So this is just some examples that for what I said before. So this is C3, and this is the one representative for the case for the toric club without first cycle, and this is for the toric club with the first cycle. This is conifold, and this is the C3 multi 3, and this is the quiver and the superpotential pair here, and this one has 2 colors, and this one has 3 colors here. So this is the corresponding periodic quiver here, and this is some colored crystal configuration here. Yeah. So if there are questions, please just stop me and ask. So let me explain a bit in detail how to build these BPS crystals. So let me give you the C3 example. So so to do this, I draw this periodic quiver on the R2. So here I only draw this few section, but you should consider this as covering the entire R2. So first, you take an arbitrary atom or other arbitrary vertex, and you consider that as your origin. And then for each path from the origin, that corresponds to an atom in your crystal. So there's this rule, the so-called melting rule. So which says if a atom is not in your crystal, then any atom that's connected from this first atom by some error also shouldn't be in your crystal. So this So this is the first atom, and this 3 is the 3 atom that correspond to these 3 paths. And then there's so this 3 atom correspond to this 3 paths here. And for example, this atom here correspond to this path or this path. So equivalently, I mean, you can reach this crystal. You can take these 2 different paths. So and then this melting rule means so this is an example of the melting rule. For example, this atom. So the precursor is already, there's only one precursor here is already exist in your crystal. So you can add this last atom here. But for this guy here, has 3 precursor, but only one of them is present in the crystal. So you cannot add this. You cannot add this one. So you can see this if you consider as the plane partition configuration. So this is one allowed configuration, but this guy is not. So from this definition, you see that we can give the coordinate to the atom, which is so because this is a path. Basically, the coordinate is the so you give some weight, which turned out to be the equivalent weight to each arrow. So the equivalent weight of the atom is just a sum over all this equivalent weight of the atom along this path. So because to reach each atom, you can have a different path to reach the atom. So for this atom to be well defined, you need some you need to declare some equivalence of the path. So for this coordinate function to make sense, so then you need the loop constraint. So for along each loop, the sum over the equivalent weight has to be 0. So this you can see from here that this loop constraint correspond to the F term, exactly correspond to the F term constraint. For example, this from if you consider this field phi b to a, so it appears in 2 loops. So that means that there are 2 terms in your superpotential. So this F term relation just means that this 3 products, this product of these 3 is equivalent to this one, which is equivalent to this loop constraint between these 2 loops. So the final ingredients is the definition of the depth. So to reach one particular atom, so you can to start from the origin, you can reach this atom by different paths. But you can also go along loops for a few times. So when you go along loops, you actually go deeper into your crystal. So that depth is just correspond to how deep you reach into the 2D crystal. So basically, this periodic quiver is the 2D projection of the 3D quiver. So this equivalent weight give you the coordinates on your 2D this 2D projection, but the depth measures how deep it is inside the 3D crystal. So for example, this guy is the first atom in your plane partition, first box. So it has depth 0. So and then this guy, this yellow one here. So to reach here, you have to go along one loop here. So correspondingly has depth 1. So this is another illustration of this definition of depth. So if you just continue this way, you can build the entire set of plane partitions. So another so okay, this is a summary. So you just follow this prescription. You can build the entire 3D crystal, and where you start from the 3D crystal, you do a 2D projection. You can reproduce this periodic quiver, and this for each area with assign equivalent weight of the corresponding chiral field. And this H of a box A, that's the equivalent weight of this particular atom. So you can also count how many independent equivalent parameters are there. So to start with, for each arrow in your quiver, there's one parameter. So as we mentioned already, there's this loop constraint. So the number of the loops this is given by. So the Q2 is number of phases in your periodic quiver. So it's the number of phases minus 1. So and then you get this the number of independent parameters after imposing the loop constraint. And then, so this loop constraint corresponds to the global symmetry. So there's also some gauge symmetry that correspond to the vertex. So in this talk, for simplicity, we're going to impose this the vertex throughout. So if you impose both the loop constraint and the vertex constraint, the number of the equivalent parameters is precisely 2. So which is what we expect. So another clarification of the terminology. So usually when we say in the literature, we also in the second part of the talk. So sometimes when we say crystal is the full crystal, when we describe the shape of that's when in some sense you just grow this crystal to all the way to infinity, you get the infinitely large crystal. And this molten crystal is a finite part that is or the finite bit that's near the origin where you kind of peeled off. So this is an example of the resolved conical. So this is the full crystal. And this one is you first grow this one. So currently you can think of removing this first atom from the full crystal, and this the second the first excited state and second excited state, and then the third one, first one. So each one has some certain charges. For each one, it corresponds to a certain combination of the D2 D0 charge. So this is another example. This is the full crystal of the this suspended pinch point singularity. And so this guy has 3 colors. So we have a white, gray, black. And then this is a particular molten crystal configuration. This is the finite bit. So in this talk, when we say we grow a crystal, we just we mean this molten crystal picture. So now, this I just finished describing this BPS states in terms of molten crystals. Now I'll explain how to use this information to construct the quiver Yangian as a BPS algebra. So because for the C3 the answer is known. So let me first explain how the C3 works, and then I generalize to generate torical labial. So this is the C3 data, and so this is the quiver, and this is the superpotential, and this is the corresponding periodic quiver. So in this case, the loop constraint is the same as the vertex constraint, which is just the sum of H1, H2, H3 equal to 0. So so this is for the molten crystal for this BPS BPS states are plane partitions. So this is the generating function, which is the Mac-Mahon function here. So this is the BPS algebra for this C3 case, which is the alpha Yangian GL1 here. So it looks a bit complicated. So let me walk you through this. So this algebra has 3 families of generators. So this phi is a Cartan, and this E is a raising operator, and this is the lowering operator. So in the definition, so we have 2 equivalent parameters. I mean, in terms of this H1, H2, H3, sum up to be 0. So the main ingredients is this cubic rational function here. So this defining relation here. So this is the Catan, and this is the relation. This is the racing operator, lowering operator. So and also the state relation. So this looks like a bit like the OPE relation of the CFT. So to convert to the mode relation, you just expand on both sides and then take the singular part. So which is this mass here. So the parameter here, the sigma 2 and sigma 3 are defined here. And so this is the relation from the singular piece. If you look at if you go a little bit to the, you can also take the first few non-singular one. This actually corresponds to the initial condition. So this relation need to be supplemented by these initial conditions, and this is the cell relation in terms of the mode. So if this is not too familiar to you, maybe it's helpful to know that this alpha Yangian is actually equivalent to the universally enveloping algebra of the W1 plus infinity. So this W1 plus infinity, so you can start by the Virasoro algebra here. So the W algebra is just a Virasoro algebra plus some conserved currents with a higher spin. So this W1 plus infinity is some particular W algebra with one generator per spin from spin 1, 2, 3 all the way to infinity. So so once the spectrum is fixed, this whole algebra is actually, the whole algebra relation is fixed. And there are only two parameters. One is the central charge. One is the first OP coefficient between the spin 3 to the spin 4. So roughly speaking, so this dictionary from this alpha Yangian GL1 to the W1 plus infinity is in terms of this mode. So roughly speaking, if you write out this modes of the W field like this, so this is spin 1, 2, 3 all the way to infinity. So this line is the zero mode, and this is the minus mode, and this is the plus mode. So so roughly speaking, this all the zero mode map to the Catan of the alpha Yangian, and the minus mode map to the E generators, and plus mode map to the F generators. And these two parameters, sigma 2, sigma 3, or H1, H2, H3, with the constraint that H1 plus H2 plus H3 equal to 0, map to the two parameter of the W1 plus infinity. So this is the action of the GL1 on the plane partition. So so here's the main ingredients. So for each plane partition, it's an eigenstate of this family of Catan. So the whole point is that this once you're given this plane partition, the eigenvalue of this phi is very easy to write down. So you have one factor that coming from the vacuum. Basically tells you how to start going your plane partition. And then for each box inside your plane partition, you have a factor of this phi 3 function. So the phi 3 functions gets shifted by this by the equivalent weight of the particular box. And then the E generator acts a box on all the allowed positions, and the F generator remove a box from all the allowed positions. So the whole point is that all these coefficients are completely fixed by the eigenvalue of this plane partition. So here, so the coefficients from this residue. So the residue, so which means that residue of this eigenvalue encodes the position on where you can add a box or remove a box. So in particular, so all this is automatic. So you start from the vacuum, you apply the E, so then you can generate the all possible plane partitions automatically. Or you start from any plane partition, you apply F, or repeatedly, you can bring it back to the vacuum. So all the poles of this phi has a meaning. So it's either means that you can add or remove. So for this to make sense, that means this all the the poles of this eigenvalue function can only be near the surface of the plane partition. So basically means that when you do this, all the Elting rule I mentioned earlier has to be automatically satisfied. So for so the main ingredients that make sure this works is this bounding factor, this phi function, and then the loop constraint. So I have so this is how it works. So you start from the vacuum and you look at the chart function and look at this pole. So it's pole 0. So that means that you can add box there, and so for each pole you can only use it once. So if you use it to add box, then you cannot use it to remove one. So that means there's no removing pole. So which means that when you apply F on the vacuum, you get 0. And then for the next level, this is the initial state. You have two factors, one for the vacuum, one for the phi function, and you have 4 poles. So this pole is the removing pole for F, which means this 3 poles is adding pole for E. I see I'm running over time, so I'll skip through this detail. Maybe just to mention that, for example, here the melting rule. So these two, so the initial states are these 2 blue boxes. So you cannot add this gray one. So this you can see by looking at this chart function. You just don't have the poles to add this 2. But if you have if you have a third box here, then you see that they give you a new pole, which is this guy here, which means that now you can add this fourth atom, but this one you still cannot. So now I want to generalize this alpha Yangian GL1 to the general quiver Yangian. So for the generator, so before I have 3 families, the Cartan and the raising operator and the lowering operator. So and now for each color, I have a family. So I also so before I know this expansion, they start from 0 here. Now to start with, I'll just leave it. I'll just be agnostic here. So I want to fix the algebraic relations here. So to do that, let me try to fix the action of the quiver Yangian on the corresponding set of color crystals. So this is a very natural generalization from the alpha Yangian GL1 case. So still for each crystal state, it's still an eigenstate of all the Cartan generator. So for each atom, it contributes a factor. So this is unfixed yet. This is some bonding factor here. I just write it here and I will fix it later. So the position is still encoded by this the sum over all the equivalent weight on the error. So again, we want the action to be controlled by this chart function here. We also want the fact that when you apply the E repeatedly on the vacuum, you can generate all the color crystals, and when you apply F on any crystal, you can bring it back to phi. So that means that again, this means that if you look at the poles of the chart function of a arbitrary crystal, all the poles have to be near the surface. So so then you see that for this to work, the bounding factor has to be chosen this way. So it's a bounding factor from B to A. So so you look at your quiver diagram. For each arrow from B to A, contribute a denominator, and for each arrow from A back to B, contribute a numerator. And then we still need this loop constraint to work for this melting rule to work. So I explain this. I'll show that this works using the simplest the example, which is this C2 mod Z2 cross C. So this is the quiver and the superpotential, and this is the periodic quiver. And again, this is the so this looks almost the same as the GL1 case, but except that now you have 2 different types of color. and the vertex loop constraint again give you h1 plus h2 is equal to 0. And then from this the quiver, you can read off the building blocks of the charge function, which is given by these 4 bounding factors. So this is the how this colored crystal looks. So it still looks like a plain partition, just with different colors. So the color scheme is the first one is so we always start from 1. So 1 here we use blue. So and then along the x1 x2 direction the color alternate, and when you go to the x3 direction the color doesn't change. So that corresponds to this the projection of so this correspond to this periodic quiver. So now you just you can check the first few cases. So this is the vacuum. So now for each color you have a charge function. So this the vacuum charge function. This is 1/z. So you have a 1 pole for the color 1. So that means that you have an adding pole for the blue atom. So it means that you can add a blue atom here, but there's no pole for the red atom. So it means that you can't add a red one for at this step, and then there's no removing poles. And then this the next level. So the initial state is this 1 atom state, and this the 2 charge functions. Again, you can look at the positional poles. So this the for the blue one. So you have 2 poles. The first pole is a removing pole for the existing atom, and then there's 1 adding pole, which is the atom along the x3 direction. And then for the red one, you have 2 poles, which are both adding poles, which correspond to these 2 red atoms here. So then you can just repeat this, and you can check that it works, and all this the melting rule also automatically works. So so this is the summary for this action. We see that as long as we choose this bonding factor here and the loop constraint, the poles. So when you add this atom, the poles always push to the surface of crystal, so that the melting rule is automatically implemented. So from this is the summary of the action of this quiver Yangian on this. Of this algebra on this BPS crystal. From here, you can also read off the expansion of the modes. So from this ansatz, you see that the expansion of the E mode and F mode doesn't change. And so because I haven't, because this bonding factor in general is some rational function. So now you see that this mode expansion can start from the -infinity. And then so when the Clavier has no compact Fourier cycle, this the quiver is non-chiral. So that means for each arrow from A to B, there's also an arrow back from B to A. So that means that this bonding factor is always homogeneous. So for the Clavier without the compact Fourier cycle, this expansion is bounded from below. So now we write down this algebra's action on this set of BPS crystals. So now from this, you can actually reconstruct how the algebra relations. So basically, you know how 1 operator acts on this states. So now you apply 2 operators, and then you exchange the order, and you compare the 2 sides. And you see actually is very simple. So now we just reproduce this entire this quadratic part of the algebra here. So basically, there are just 2 types of ingredients. One is coming from this bonding factor. The other is this statistics factors, which is also just given by the quiver, which basically counts how many self loops for the vertex. So now if you want the mode relation, you just expand this this OP type relations here, and then you compare the singular terms. So this the full set of relations here. So for the Tori so for the Tori club EL without the compact first cycle, this alpha Yangian constructed this way is actually just this alpha Yangian of a super Lie algebra, GLMN here. But for the case with the compact first cycle, this seems to be a new family of algebras. So I explained how to derive this quiver Yangian by looking at the actions on the crystal. So this is the paper with Masahiro Yamazaki, and later this is also confirmed by the equivariant localization computation from the input for quiver quantum mechanics by Dima and Masahito. So now I'll go to the representation part. So until now, the quiver I use is actually the canonical frame quiver. So remember, we always choose a particular vertex to start going your crystal. So that correspond to so you have a framing node which correspond to the D6 or all these other non-compact D branes. So you have a one arrow going from this framing node to one particular vertex. So that particular vertex is where you start your crystals. So this is the C3 case, and this is the C2 multi 2 cross C case. So in our convention we always label the frame nodes as one. So they correspond to the vacuum representations. So correspondingly, so if you remember, so this is the action here. So there's one factor that comes from the vacuum. So this guy determines how the first atom that you can grow. So this the pole is always the pole for the charge function, the color one here. So that means this vacuum charge function is given by this this guy. So and then the full crystal that you can grow from this, we call this canonical crystal here. So any questions here? So this is the connection from all this concept I mentioned for this stuff that's appeared until now. So we have this canonical crystal, which is basically given by this the vacuum charge function. So starting from the vacuum charge function, you can grow this canonical crystal, which corresponds to the canonically framed quiver, and which is give you which correspond to the vacuum representation of the quiver Yangian. And from this, you can bootstrap the quiver Yangian. In this case, we call it unshifted to distinguish from the later the shifted one. And this give you the BPS algebra of the corresponding quantum mechanics system. So now the question is how to generalize this to the other representations. So the hint is that we can change the shape of the crystal. So the hint come from we can look at the other types of BPS counting system. For example, we can look at other chambers. We can include open BPS states. So we see that all these other crystals are some subcrystals of the canonical crystal. For example, this is the canonical crystal. So this is the finite state here, and so this shape just means that if you go this infinitely, so you reach so this one should be infinitely large. But this gives you the shape of this the infinite crystal. But you can also have the non-trivial symptotics along these three directions given by the three Young diagrams. So this is one example. This is the ground state, and this is the excited state. So if you look at this ground state, the complement this will be a subcrystal of the canonical crystal. So the canonical crystal fills this entire octet. So the complement of this guy here will have this blue bit missing. So this complement this is the subcrystal, and we want to describe the shape of that subcrystal, which contain the information of this representation. So another example is this resolved conifold here. So this is the canonical crystal for the non-community DT chamber, and this is some infinite chamber with so this is labeled by the number of the white atom on this ridge. So this is m equal to 3, and this is you can also have finite chambers. So you start from this one and cut like this, you get a finite one. So the point is that both these crystals are subcrystals of the canonical crystal. So, so you see that all these other interesting situations are subcrystals. And we want to go one step further. So we want to describe generic subcrystals that correspond to the irreducible representations. So the question I want to ask is first how to describe the shape of the subcrystal, and then how to translate this to the Guangxi chart function. So as we mentioned earlier, this the Guangxi chart function determines the entire representation, and then how to translate to this to the framing of the quiver, and then how does this change the algebra? So so now this is the full canonical crystal, and this is some particular subcrystal. So so to describe the shape of this subcrystal, it turns out we can think of it as a superposition of some negative and positive and negative canonical crystal. So you see that this guy, you can think of this as you first so to determine this decomposition, there are a few steps. So the step one is that so there are two tips. So this determines the starting point of the positive crystals, which we call starters. And then you let these two positive crystals grow, and then they'll intersect. So and then when they intersect, so then there will be an overlap. So you don't want to overcome them. So you want to add some negative crystal to compensate you want to add some negative crystal to kill off this overlaps. So then this will be called negative crystals. So the starting point of the positive crystal we call starters, and this is called pulsars because it's slow down the growth. So and then but then for this example, you have 3 positive crystals. And then this is the intersection of the first 2, and then this intersection first 2, and then intersection of the second and third, and this the intersection of the first and third. So you want to remove these 3 negative crystals, but then you see that this first crystal and the first negative crystal and the second negative crystal also start to overlap. So then you want to add the overlap back in order to compensate this overlap. So you just continue like this until you reproduce the entire subcrystal. And after this is done, you can do something more. But this is optional, so you can truncate whatever you have now by adding some negative crystal. For example, this shape, you can think of this having one positive crystal here and then a negative crystal here. So the starting point of negative crystal we call stopper here, because if you put the stopper here, then this crystal will just stop growing once you reach this part. So the point is that you can create arbitrary simply connected subcrystal this way by placing the your initial starters and stoppers. So the pulses you can determine from these starters. So this is an example that for the case we considered before. So this is the open BPS states with these 3 asymptotics. So you look at the projection of this, and you see where the the positive and negative crystals have to be here. So this black part, black dots, they are starters, which is the starting point of the positive crystals, and this white bits, so-called pulsars, which are starting atom of the negative crystals. So you can have overlaps of 2 positive crystals, and for this guy here is overlap of 3 positive crystals. So which means that so you have to take into this account when one negative crystal corresponds to the overlap of the 3 instead of 2. So this is another example for the conical. So to build this subcrystal from the original canonical crystal, so you need 3 positive crystal starting from these 3 starters, and then they overlap already at the next layer. Then you need to cancel those. So that means that you need to add some negative crystals starting this 2 black dots, black atom here. And then for the finite chamber, that means that you just add some stoppers here at these 2 points to stop it, to stop the crystal from going along these 2 directions. So any questions here? So now for this subcrystal, the action of the quiver Yangian, the only change is in this ground state chart function. So instead of this factor 1 over z, now you need this more complicated rational functions. So for each starters, you have a pole in this ground state chart function, and for each pulsar and stopper, you have a 0. So the pole you understand. So it just when you see a pole, you can at the initial at the first state, you can add an atom at the position of those poles. So the pulsar or stoppers upstairs, it just means that you cancel. When you reach there, when you have some pole that correspond to the place where you can add the atom, but if you have a 0 here, you cancel those so that you can. So either you stop there, or it make the go slower. So from here, you can see that you also change the mode expansion of this carton here. So so this is the change. So we define this shift, which is given by the difference between the number of factors in the denominator and the number of factors in the numerator. So they change the expansion here. So from the chart function to the frame quiver, there's also a clear procedure. So for each starting atom, for each starting atom of the positive crystal, for each starter, we need to add arrow from the Fermi node to that node, and then for each starting atom of negative crystal, you need to add arrow from this vertex back to the Fermi node, and then you need to add corresponding terms to the superpotential to make this all consistent. So this is some example here. So now you see that for the general subcrystal, this relations here. So for generic subcrystal, in particular the simply connected and that correspond to the irreducible representation, it corresponds to some ground state chart function. And from here, when you apply all these generators, you can grow the entire representation. So this representation also you will change this mode expansion. So it's enter inside this definition of the quiver Yangian as a shift. So then they correspond to this framed. framed quiver and correspond to the BPS algebra of this quiver quantum mechanics with this framed quiver and superpotential. So let me now summarize. So for a generic toric Clavier threefold, we consider the BPS sector of the deep brain system of the type 2A string on this threefold. And we start from this effective description of the quiver quantum mechanics and sees that the BPS states are given by the set of color crystals. And from the action of the BPS algebra on these color crystals, we can basically bootstrap the algebraic relations. So the resulting algebras are some quiver Yangian. And you can also bypass this step and just start from this the quiver superpotential pair and write down this algebra immediately. So this is the final answer. So the ingredients that come from this the quiver is just this bounding factor and this staticity factors here. So this the algebraic relation. You see that this is very explicit and it works for all toric Clavier threefold. So for the first part, I explained the case when this quiver and superpotential is canonically framed, which correspond to the closed BPS state and the non-commutative DT chamber. So the crystal are the molten crystals from the canonical crystal and gives the vacuum representation of this BPS algebra. And the second part, I looked at the generic subcrystal of the canonical crystal and showed that they correspond to the non-vacuum representation of the shifted quiver Yangian. And the shape of this subcrystal correspond to the framing of the quiver. And then, so this cover all the non-BPS counting problems, and also we can also see that you can create almost arbitrary shape for the subcrystal. So this is the this relation between the things that I mentioned here. Okay, so future directions is so the procedure I described is in this colored crystal. You see, we use this color crystal. So this basis you can think of as a color crystal basis, but you can also imagine doing this using some other basis of the algebra. For example, because you know that for each, so you can consider the generic toric Clavier as take a C3 and then glue this trivalent vertex from C3 together to make the bigger, more complicated toric Clavier. And so you can think of this BPS algebra as glued by this the building block from the C3. So for each vertex is alpha Yangian G1, and for each internal leg, that gives you a additional generator, which is a bimodule of the two alpha Yangian G1 at these two ends. So so the result in this gluing construction is known for this for the simplest cases. So it might be interesting to see whether to make it work for more complicated cases. And also maybe it's useful to translate to the W algebra basis and also to study the truncation of the algebra, which correspond to adding the non-zero D4. And this can potentially produce a new rational VOAs. And also it will be important we want to compare to other systems. So, and then more generally, we would like to know what's the meaning of this, all these new subcrystal representations. I mean, what kind of accounting problem they appear, and then maybe generalize to non-toric Clavier, or also to relate to the BPS algebra that you see in other systems. Yeah, that's it.
Okay, thank you so much, Wei. So, okay, now the floor is open for questions or comments. Anything? Yeah, even elementary questions are welcome.
Okay, I'll ask a question.
Yes, please.
So you mentioned that in the case of compact 4-cycle being present in the toric Calabi-Yau threefold, firstly, the quiver Yangian is new. I'm just trying to understand the main differences from the case without the compact 4-cycle, because there I believe that your affine Yangian is that of, in general, for example, for a suspended pinch point, it corresponds to GLMN. And so basically, my question is, how does the algebra generalize? What are the differences? For example, the mode expansion has negative integer values. Is there any other difference?
No, that's the main difference.
Okay.
Yeah, so that's also related to whether the quiver is chiral or non-chiral, which she mentioned in the passing. But, yeah.
Yeah, I mean, I think one surprising thing is this in this construction, actually, the difference between the case with or without 4-cycle is actually not. I mean, all this. I mean, for example, here you don't see the difference. I mean, they work in a very unified manner. So the difference only comes in from this binding factor here. And another thing is that yeah, but much less is known for the case with the compact 4-cycle. For example, for the case without compact 4-cycle, the cell relation is also known. So once you include the cell relation, then the vacuum character of this Yangian reproduce exactly the counting of the crystal. So it's kind of important to fix all these cell relations. But for the I mean, for the case without compact 4-cycle, the algebra is given by this. I mean, they also the cell relation is also known. We can check that it works. But for this one, I mean, we kind of know a procedure how to fix it, but it's not very efficient.
Thank you.
Any other questions or comments?
Maybe one more question, if there's
Yes.
no one else.
Yeah, sure. Go ahead.
Is there some notion of understanding how the the quiver Yangian maybe changes as the system undergoes wall crossing? For example, from the non-commutative DT chamber to some other chamber. Can we have a handle on that?
So in this house, I went a bit in a roundabout way. So I first considered the representation. So for example, so this non-commutative DT chamber. So this so the m equal to 1 means that at the first level you have one starting atom. So this is another chamber which has 3 starting atoms here. So I just first show that both of this has to be the representation of some quiver Yangian. So and then I show that they're essentially the same quiver Yangian except for the shift. So basically they have this. So they have different representation. So they have different Guangxi chart function, and this Guangxi chart function, because it entered the chart, the full chart function. So full chart function, I mean, which is the eigenvalue of your Cartan. So it changed the mode expansion of the Cartan. So so they're essentially the same quiver Yangian, but except for that they have different shift. So I think in the terminology, one is has -1 shift, the other is -3. Yeah, but yeah, that's basically when you cross the wall, you change at the algebra level, you only change this mode expansion here, and you change the representation.
I see. Thank you.
Okay, great. So any other questions? Yeah, in fact, generally these are new algebra. So I see some mathematicians in the audience. So I really appreciate if you get some comments from the mathematician. Maybe not now, but in the future. Okay, so if there are no further questions, let's thank Wei again.
Thanks.
And